For as long as we've gazed up at the stars, humanity has asked one burning question: are we alone? That primal curiosity pulses through our history, from ancient myths about gods in the heavens to the first radio signals beamed into the cosmos, carrying our hopes like messages in a bottle. And now, after centuries of searching, we might finally be on the verge of an answer. Imagine turning the pages of a cosmic detective story where every clue brings us closer to solving the universe's greatest mystery, and today, we're diving into 30 of the most jaw-dropping discoveries that could rewrite everything we thought we knew about life beyond Earth. From the icy plumes of Enceladus to the eerie dimming of distant stars, the universe is whispering secrets in ways we're only beginning to understand. Scientists are uncovering bizarre chemicals in alien atmospheres, spotting strange structures around far-off planets, and even detecting signals that defy explanation. Some of these findings are so unexpected, they've left researchers questioning the very laws of nature. Others hint at possibilities so thrilling, they blur the line between science and science fiction. But here's what's wild: every single one of these discoveries is real, documented, and packed with clues that could lead us to the ultimate revelation. This isn't just about aliens in pop culture or little green men in flying saucers. It's about the mind-bending science behind what life might look like in places we once thought were barren wastelands, worlds drowned in molten lava, bathed in radiation, or hidden beneath miles of ice. It's about the technology that's letting us peek into the chemistry of planets light years away, and the strange, almost poetic ways the universe might be signaling to us. And most of all, it's about that electrifying moment maybe coming sooner than we think when we finally stumble upon proof that we're not the only ones asking these questions. So buckle up. By the end of this journey, you'll never look at the night sky the same way again. Picture a world shrouded in thick, toxic clouds where acid rain falls from a sky choked with sulfur. Venus has long been dismissed as a hellscape: boiling temperatures, crushing atmospheric pressure, and no chance for life as we know it. But in 2020, something impossible flickered into view. Scientists detected traces of phosphine gas swirling high in Venus' atmosphere, a discovery so unexpected it sent shockwaves through the scientific community. Here's why it matters. On Earth, phosphine is almost exclusively linked to living organisms. Tiny microbes in swamps and even inside animal guts produce it naturally. No known non-biological process on Venus should create this gas in such abundance. So when telescopes picked up its signature, the immediate question was clear: could this be our first whiff of alien life? But Venus isn't making it easy. The planet's surface is a volcanic nightmare, and some researchers argue that unknown geological activity might explain the phosphine. Maybe undiscovered chemical reactions are at play deep in those swirling clouds. Yet others point out that even the most extreme volcanic models struggle to account for the sheer amount detected. The debate rages on, and that's what makes this discovery so thrilling. Either we're looking at an entirely new type of geological process defying our understanding of Venus, or we've stumbled upon something far more extraordinary. Microbial life floating high above the planet's deadly surface, surviving in droplets of water suspended within the acid clouds. If that's true, it means life could be tougher, weirder, and more adaptable than we ever imagined, hiding in places we once thought were utterly inhospitable. If life does exist in Venus clouds, it would rewrite the rules of biology as we know them. The upper atmosphere where phosphine was detected is a world of extremes. Temperatures hover around a relatively Earth-like 86 degrees Fahrenheit, but the air is saturated with sulfuric acid, creating droplets 100 times more corrosive than battery acid. And yet, Earth has shown us that life thrives in the unlikeliest places. Microbes here survive inside nuclear reactors, in boiling hot volcanic vents at the ocean floor, even in the dry valleys of Antarctica where conditions mimic Mars. Could Venus cloud dwellers be just another example of nature's stubborn creativity? Some scientists point to Earth's acidophilic organisms, like the bacteria that thrive in the bubbling, toxic springs of Yellowstone. These extremophiles have evolved to not just endure acidic environments, but to harness them for energy. If similar microbes floated in Venus' atmosphere, they might use sulfur compounds the way plants use carbon dioxide, turning poison into fuel. But Venus adds another twist. Its clouds are perpetually moving, swept by hurricane-force winds that could disperse life across the planet. Unlike Earth's surface-bound ecosystems, these hypothetical microbes would live a nomadic existence, riding atmospheric currents in a never-ending cycle. NASA's upcoming JWST mission could finally give us answers. Slated to plunge through Venus' atmosphere in the late 2020s, the probe will analyze chemical composition in real time, hunting for organic molecules or even structural hints of microbial life. Meanwhile, private initiatives are proposing cloud-based balloon missions designed to linger in the habitable zone, sampling droplets directly. The challenge: Venus' corrosive environment eats through metal and electronics within hours. Any mission will have to outsmart the planet itself, a technological hurdle as daunting as the science is thrilling. The implications stretch far beyond one planet. If life clings on in Venus' hellish skies, it suggests the universe could be teeming with organisms in places we've written off as sterile. Gas giants with turbulent atmospheres, ice moons with subsurface oceans suddenly, every wild possibility seems back on the table. And that's the real magic here. Venus, long considered a cautionary tale of runaway greenhouse effects, might just become our greatest teacher in the search for life. Whether the phosphine mystery ends with microbes or some bizarre new chemistry, one thing's certain: we're about to learn just how inventive the cosmos can be. Deep beneath the icy crust of Saturn's tiny moon Enceladus, something extraordinary is stirring. A hidden ocean warmed by the moon's restless core, where plumes of water erupt into space like geysers. When NASA Cassini spacecraft first spotted these towering jets in 2005, scientists were stunned. Here was a moon barely 300 miles wide, yet it was shooting material hundreds of miles above its surface, creating one of Saturn's shimmering rings. But the real shock came when Cassini dove through those plumes, tasting their chemistry, and what it found changed everything. The spacecraft detected organic molecules, the building blocks of life, alongside molecular hydrogen and tiny silica particles. Together, these clues pointed to one jaw-dropping possibility: active hydrothermal vents on the ocean floor, where superheated water erupts through rocky fissures rich with minerals. On Earth, such vents are oases of life in the abyss, hosting bizarre creatures like tubeworms and blind shrimp that thrive in total darkness, fueled not by sunlight but by chemical energy. If Enceladus has these vents too, could its dark ocean also harbor life? The parallels to Earth's lost city hydrothermal field are uncanny. Discovered in the Atlantic Ocean in 2000, this otherworldly landscape of towering carbonate chimneys spews warm, alkaline fluid, a perfect cocktail for fostering microbial life. Like Enceladus, it operates entirely independently of the sun, powered by reactions between seawater and rock. The similarities don't stop there. Both environments have the key ingredients life needs: liquid water, an energy source, and organic compounds. On Enceladus, tidal forces from Saturn's gravity keep the ocean from freezing, flexing the moon's core to generate heat. That constant churning could mean these vents have been active for billions of years, plenty of time for life to emerge. Yet Enceladus adds its own twists. Its ocean is global, sealed under an ice shell up to 20 miles thick, with pressures far greater than Earth's deepest trenches. Any organisms there would need to adapt to perpetual darkness and crushing weight. Then there's the plumes themselves, violent ejections that blast material into space, offering a free sample of the ocean below. Future missions could fly through these jets, analyzing them for even more complex molecules like amino acids or lipids, which would strengthen the case for biology. The implications are staggering. If life exists in Enceladus' underground sea, it would prove that liquid water, not sunlight, is the universal prerequisite for biology. Suddenly, ice-covered moons across our solar system, from Jupiter's Europa to Pluto's frozen heart, become prime real estate in the search for aliens. And that's the real magic of this discovery. Enceladus isn't just a curiosity, it's a blueprint showing us where and how to look for life in the cosmos. Every plume it fires into the void is a message written in chemistry, whispering that we might not be alone after all. Those plumes erupting from Enceladus aren't just cosmic fireworks, they're a free delivery service from the moon's hidden ocean, spraying its secrets into space where we can reach them. That's why scientists are racing to design missions that could catch these icy geysers in the act, sampling them for the most tantalizing clue of all, amino acids. These organic molecules are the Lego bricks of life, stitching together to form proteins in everything from bacteria to blue whales. Finding them in Enceladus sprays would be like discovering a factory floor where the universe assembles life's raw materials. Here's the kicker. We've already spotted methane and hydrogen in those plumes, two ingredients that could power entire ecosystems without sunlight. On Earth, microbes clustered around deep sea vents thrive on this exact chemical cocktail, munching on hydrogen and carbon dioxide to produce methane as waste. The ratios detected on Enceladus match what we'd expect if similar organisms were churning away beneath its ice. It's not proof of life yet, but it's a flashing neon sign pointing to where we should look next. Now imagine a spacecraft swooping through those plumes, its instruments inhaling droplets that haven't touched sunlight in billions of years. The European Space Agency's Titan Dragonfly mission, originally designed to buzz across Saturn's hazy moon, could be retasked to make a pit stop at Enceladus. Picture a drone-like craft diving through the jets, its sensors hunting for amino acids with telltale imbalances, molecules that lean left-handed, a hallmark of biological activity. Earth's amino acids overwhelmingly favor this orientation, a quirk thought to stem from life's earliest stirrings. If Enceladus molecules show the same bias, it would be hard to dismiss as random chemistry. But the ocean moon isn't giving up its secrets without a fight. Sampling plumes sounds simple until you account for their speed, over 1,000 miles per hour, fast enough to sandblast delicate instruments. Then there's the ice itself, peppered with jagged outcrops that could shred a probe on descent. Engineers are brainstorming solutions, armored collectors that snap shut like clamshells, or lasers that vaporize particles mid-flight for instant analysis. Every challenge feeds the thrill of the hunt, because what's at stake isn't just data, it's the chance to answer whether life is a cosmic fluke or a routine miracle. While we wait for missions to launch, telescopes are already scouring the plumes from afar. The James Webb Space Telescope recently trained its gold-plated eye on Enceladus, seeking complex organics that Cassini couldn't spot. Early data hints at molecules heavier than methane, chains of carbon that could form the backbone of cell membranes. Combine that with the moon's steady heat source and salt-rich waters, and you've got a recipe that looks eerily familiar. After all, Earth's life didn't start in tropical lagoons. It likely clawed its way out of similar volcanic chaos. The beauty of Enceladus is how it turns assumptions upside down. A moon smaller than Iceland shouldn't have the energy to sustain a global ocean, let alone geysers that dwarf Earth's tallest waterfalls. Yet here we are, staring at a place where the impossible seems to happen routinely. Whether its depths hold fish-like creatures or just hardy microbes, one truth is inescapable. Enceladus has rewritten the rules of where life can exist. And with every plume it fires into the void, it lobs another challenge at us daring science to catch up with its mysteries. Beneath the cracked, frozen surface of Jupiter's moon Europa lies an ocean so vast it could drown Earth twice over. This isn't science fiction. Hubble's telescopes have captured towering plumes of water vapor bursting through the ice, some reaching over 100 miles high, as if the moon itself is exhaling secrets into space. Each eruption carries traces of sodium chloride, plain old table salt, a tantalizing hint that Europa's hidden sea might be startlingly similar to our own. What makes this discovery so electrifying is the sheer scale of possibilities. Europa's ocean isn't just a stagnant pool, it's a dynamic, churning world, kept liquid by the relentless gravitational tug of war between Jupiter and its neighboring moons. This tidal kneading generates enough heat to melt ice into an abyss deeper than Earth's Mariana Trench, with potential hydrothermal vents dotting the ocean floor like underwater volcanoes. On our planet, such vents are biological hotspots, teeming with organisms that thrive on chemical energy rather than sunlight. If Europa has its own version of these oases, the chances of finding life there skyrocket. But the moon isn't giving up its mysteries easily. Its icy crust, up to 15 miles thick in places, acts like a cosmic vault door, shielding the ocean from direct observation. Yet those geysers are master locksmiths, offering a backdoor entry. When Hubble analyzed sunlight filtering through the plumes, the spectrum revealed the unmistakable fingerprint of salt. Not just any salt, but the kind that suggests rock-water interactions at the ocean's core. In other words, Europa's waters might be leaching minerals from a seafloor as complex as Earth's, creating a broth of nutrients ripe for life. Enter the Europa Clipper, NASA, a most ambitious alien hunting mission yet. Slated to launch in 2024, this spacecraft won't land on the icy moon. Instead, it'll perform over 40 close flybys, skimming just 16 miles above the surface to sample those geysers with instruments sensitive enough to detect fatty acids or even strands of DNA-like molecules. One tool, aptly named the surface dust analyzer, will catch tiny ice grains ejected by the plumes, scrutinizing them for organic material. Another, a thermal imager, will map the ice shell's thickness, pinpointing the best spots for future drills or submersibles. The stakes couldn't be higher. If Clipper finds molecular structures that mirror Earth's life, even something as simple as a lipid membrane, it would suggest the universe has a playbook for biology, and Europa might be following it. But there's a twist. Life here could be utterly alien, relying on chemistry we've never seen. Sulfur-based metabolisms, silicon backbones. The moon's extreme conditions might have spawned organisms that redefine what life even means. That's the double thrill of Europa. It's not just about finding life, it's about discovering how creative life can be when handed a blank slate. With every plume it sprays into the void, this icy moon taunts us with a challenge. Dive in, it whispers, and see what's waiting in the dark. Europa's icy shell isn't just a smooth, frozen wasteland. It's a fractured puzzle of chaos terrains, regions where the surface has collapsed into jagged blocks and ridges as if some colossal force shattered it from below. These bizarre formations might hold the key to unlocking the moon's deepest secrets. Picture Antarctica's ice shelves calving into the sea, but on an alien world where the cracks expose something far more extraordinary. Thin, permeable ice that could act as windows into the ocean below. Scientists believe these chaotic zones form when warm water from Europa's subsurface sea rises, melting and destabilizing the ice above. Some areas might have ice just a few hundred feet thick, paper-thin compared to the miles of frozen crust elsewhere. That's a game changer for potential life. Organisms or organic material from the depths could get funneled upward through these fractures, carried by convection currents like nutrients rising in a cosmic soup. Suddenly, we wouldn't need to drill through 15 miles of ice to find clues. They might be sitting right at the surface, waiting to be scooped up by a passing spacecraft. The parallels to Earth's subglacial lakes are uncanny. Beneath Antarctica's ice lie bodies of water like Lake Vostok, sealed off for millions of years yet teeming with microbial life. When scientists finally drilled into its depths in 2012, they discovered organisms adapted to extreme cold, darkness, and pressure, conditions eerily similar to Europa's ocean. Some even metabolize hydrogen and carbon dioxide, just as hypothetical Europan life might do around hydrothermal vents. If Earth's ice-bound extremophiles thrive in isolation, why couldn't Europa's? But the Moon adds its own extraterrestrial twists. Europa's chaos terrains are laced with reddish-brown streaks, possibly salts or organic compounds brought up from the abyss. The infamous Thera Macula region looks like a frozen tornado, its ice rafts twisted into spirals by forces we're only beginning to understand. Some models suggest these areas experience sporadic eruptions, icy volcanoes spewing slush from the ocean into space, a phenomenon we've already glimpsed in those 100-mile-high plumes. Each eruption could be a biological elevator, transporting deep-sea microbes to the surface where missions like Europa Clipper might spot them. The real prize lies beneath. Hydrothermal vents on Europa's seafloor could be oases in the dark, fueled by the same tidal heating that keeps the ocean liquid. On Earth, such vents support entire ecosystems of tube worms, giant clams, and ghostly white crabs, all thriving without a single ray of sunlight. Europa's versions might host even stranger adaptations, organisms that use sulfur or methane as energy sources, or life forms with silicon-based chemistries to withstand crushing pressures. The ocean's sheer size, twice Earth's combined volume, means these vents could be scattered like islands in an alien archipelago, each hosting unique forms of life. Future missions might not even need to reach the ocean to find answers. Ice-penetrating radar could map the chaos terrain subsurface structure, revealing liquid water pockets just below the surface, potential stepping stones for life migrating upward. Imagine a Europa lander scooping ice from these regions and baking it in an onboard lab, searching for the telltale gases released by dying microbes. Or a rover crawling across the fractures, its sensors tuned to the chemical whispers of organisms we've never dared imagine. This isn't just about finding life. It's about discovering a second Genesis proof that biology can spark independently in the unlikeliest corners of the cosmos. Europa's chaos terrains are more than geological oddities. They're torn pages from a story we're only beginning to read. And with every new crack we map in that icy surface, the plot thickens. Mars has a secret it's been writing across its rusty slopes, dark, finger-like streaks that appear and vanish with the seasons. These mysterious features, called recurring slope lineae, first had scientists convinced they'd struck gold, proof of liquid water trickling down Martian hillsides in the modern era. The implications were staggering. Where there's liquid water, there could be life, or at least the conditions to sustain it. But as with all things Mars, the truth turned out to be far more complicated. Early observations from orbit showed the streaks darkening and lengthening during warmer months, then fading as temperatures dropped. Spectroscopy revealed hydrated salts mixed into the soil, a telltale sign of briny water seeping to the surface. The images painted a tantalizing picture, salty rivulets oozing from underground aquifers, carving temporary pathways down sun-baked slopes. If true, it would mean Mars wasn't just habitable billions of years ago. It might still be hosting damp, if not downright soggy, pockets today. Then came the curveball. High-resolution scans revealed the streaks often start at odd points, like the tops of ridgelines where water wouldn't naturally accumulate. Experiments with simulated Martian soil showed dry sand could create eerily similar patterns as it avalanched downhill. The explanation: seasonal changes in temperature might loosen sand grains coated in dust, sending dark material sliding without a single drop of liquid involved. But hold on, this doesn't rule out water entirely. Even if most lineae are dry flows, some still exhibit chemical signatures that scream brines. And here's where it gets wild. Mars' atmosphere is so thin that liquid water should instantly boil or freeze. Yet salts could lower its freezing point, creating fleeting droplets that cling to life for just long enough to matter. Picture microscopic oases in the sand, tiny wet films where microbes could, in theory, cling to existence. Enter Perseverance, NASA's latest rover, now scouring Jezero crater for fossils of ancient microbial life. While it isn't studying the lineae directly, its discoveries could rewrite the rules. If Perseverance finds evidence that Mars once thrived with life, those modern-day streaks, whether wet or dry, become even more compelling. They'd hint at a world that never fully gave up on habitability, where life might have retreated underground, biding its time in damp crevices or salt-rich soils. The debate isn't just academic. Future human missions are counting on understanding Mars' water cycle, and those lineae could hold the key. Imagine astronauts tapping into briny seeps, turning them into drinking water or fuel. Or worse, landing near a streak only to trigger a sandslide. Every new theory peels back another layer of Mars' enigma, revealing a planet that's neither the bone-dry wasteland we once imagined nor the dripping oasis some hoped for. It's something in between, a world that keeps flirting with the idea of life, leaving us to decode its cryptic signals. So are the streaks proof of modern water? Maybe, maybe not, but they're a reminder that Mars is still an active, changing world, and the hunt for its secrets is far from over. Whether the truth lies in damp sands or hidden aquifers, one thing's clear: those dark streaks are more than just stains on a hillside. They're clues in a planetary cold case, and we're just beginning to piece together the story. Mars has been playing a gaslighting game with scientists for years, literally. NASA Curiosity rover keeps sniffing out bursts of methane in Gale crater, a gas that vanishes as unpredictably as it appears. On Earth, 95% of methane comes from living sources, from cow stomachs to swamp bacteria. So when Curiosity's sensors first spiked in 2013, the internet erupted with whispers of Martian microbes. But the red planet loves a good plot twist, because this methane behaves like nothing we've seen before. These aren't steady leaks but sudden puffs, sometimes 10 times the background levels, that dissipate within hours. One theory suggests underground reservoirs where methane produced by geological reactions gets trapped in icy cages called clathrates. When temperature or pressure shifts, these cages shatter, releasing gas that seeps through cracks to the surface. Mars' thin atmosphere would then scatter the methane rapidly, explaining the fleeting spikes. There's precedent. Earth's permafrost leaks methane this way as it thaws, but here's where biology barges back in. Some microbes on Earth, called methanogens, thrive in oxygen-free environments like deep underground or animal guts, exhaling methane as waste. If similar organisms exist beneath Mars' surface, perhaps sheltered in damp cracks or briny pockets, they could produce these erratic burps, the clincher. Seasonal patterns. Curiosity detected higher methane levels during Martian summers, aligning with periods when subsurface temperatures might coax microbes into metabolic overdrive. Enter Europe's ExoMars Trace gas orbiter, circling Mars with one mission: create a methane map so detailed it could pinpoint sources to within a few square miles. Armed with spectrometers 100 times more sensitive than Curiosity's, it's scanning for methane's chemical fingerprint across the entire planet. Early results only deepen the mystery. While Curiosity catches whiffs, the orbiter sees almost nothing. This discrepancy might mean the gas disperses too quickly for orbiters to catch, or that Mars destroys methane faster than expected through unknown chemical processes. The implications stretch beyond one gas. If Mars' methane is geological, it reveals an active planet with ongoing hydrothermal or volcanic processes we've yet to discover. If biological, it suggests life could be hibernating beneath the radiation-blasted surface, clinging to existence in ways that redefine our search for aliens. Perhaps the truth lies in between an exotic chemistry we've never encountered, where rocks and water interact under alien conditions to mimic life's signatures. Every erratic methane spike is a breadcrumb trail leading us deeper into Mars' enigma. Future drills might need to dig meters below the surface, beyond where radiation sterilizes the soil, to find answers. Until then, these mysterious puffs keep us guessing: is Mars teasing us with hints of life, or just demonstrating how clever geology can mimic biology? One thing's certain: the red planet still has stories to tell, and we're only on chapter 1. Saturn's largest moon, Titan, isn't just another frozen rock. It's a chemical factory where the building blocks of life are being assembled in ways that would make even Frankenstein's lab look tame. When NASA Cassini probe pierced Titan's orange haze, it uncovered a world where methane rains from the sky, rivers carve valleys into hydrocarbon dunes, and lakes of liquid ethane stretch for hundreds of miles. But the real shock came when Cassini analyzed the moon's soupy atmosphere, discovering a zoo of organic molecules like benzene, acetylene, and hydrogen cyanide compounds that on Earth are linked to the origins of life. Picture this: Titan's thick nitrogen-rich air is constantly buzzing with chemical activity. High-energy particles from Saturn's magnetic field bombard the upper atmosphere, breaking apart methane and nitrogen molecules that then recombine into ever more complex chains. Some of these molecules drift downward, forming a steady organic snow that blankets the surface. It's a process eerily reminiscent of Earth's ancient past, when our own primordial soup was spiked with similar ingredients. But here's where Titan flips the script: instead of water as the solvent for life, this moon offers rivers of liquid methane at -290 degrees Fahrenheit. That frigid environment raises a mind-bending question: could life evolve in a chemistry set so alien? Astrobiologists have theorized about methane-based organisms that would breathe hydrogen instead of oxygen and metabolize acetylene for energy. On Earth, certain deep-sea microbes already thrive by consuming hydrocarbons from underwater vents. Titan's hypothetical life forms might take this further, using liquid methane the way our cells use water, with membranes made from flexible acrylonitrile molecules that stay supple in bitter cold. The evidence is tantalizing. Cassini detected unusually low levels of hydrogen and acetylene near Titan's surface, exactly what you'd expect if something were consuming those compounds. Then there's the curious case of the disappearing methane. Titan's lakes should have evaporated billions of years ago without a replenishing source, hinting at possible underground reservoirs or even microbial activity recycling the gas. Yet Titan's extreme cold is both a blessing and a curse for life. Chemical reactions unfold agonizingly slowly without liquid water's catalytic help. But slow doesn't mean impossible. Some models suggest that over Titan's 4.5 billion-year history, reactions in subsurface cryovolcanic chambers could have jump-started biology at a glacial pace. Or perhaps impacts from comets delivered pockets of transient liquid water, creating temporary warm oases where reactions could accelerate. This isn't just about rewriting biology textbooks. Titan challenges our very definition of habitable zones. If life can brew in methane lakes under an orange sky, then ice moons and even rogue planets drifting between stars suddenly enter the game. NASA's Dragonfly mission, set to launch in 2027, aims to settle the debate by helicoptering across Titan's dunes with instruments designed to sniff out complex organics. Imagine a nuclear-powered drone sampling tholin-rich soil. Those organic goops formed when sunlight cooks atmospheric gases, searching for molecular patterns that scream biology rather than random chemistry. The beauty of Titan lies in its duality. It mirrors Earth's past while offering a window into how life might reinvent itself under alien rules. Every hydrocarbon lake, every whiff of complex organics, whispers the same provocative idea: the universe might not have just one way to make life. Sometimes it picks up a whole new playbook. Dragonfly isn't your typical planetary explorer. It's a nuclear-powered helicopter built to conquer Titan's alien skies. Slated to touch down in 2034, this rotorcraft will leapfrog across the Moon's methane-soaked dunes like a cosmic grasshopper, covering more ground in months than traditional rovers could in years. Its mission: to crack open Titan's greatest secrets by sampling the very ingredients that might be brewing life under conditions we've never seen before. Imagine this drone hovering over a vast field of hydrocarbon sand, its skis brushing against grains soaked in organics that have been falling from the atmosphere for eons. Each landing site is a time capsule. Some dunes are rich in Tholen's complex organic molecules forged in Titan's upper atmosphere, the same compounds that might have seeded Earth's primordial soup. Others border Selk Crater, a 60-mile-wide impact site where ancient ice melted long enough to mix with organics, creating a potential hotspot for probiotic chemistry. Dragonfly's instruments will vaporize these samples, analyzing the plumes for amino acids or lipids, the molecular fingerprints of life's building blocks. But Titan's most tantalizing features might be hidden in plain sight. Radar scans suggest cryoval, Kono's ice-spewing mountains dotting the landscape, their eruptions potentially replenishing the surface with fresh organics from deep underground. Picture a slow-motion eruption, not lava but a slurry of water, ammonia, and methane oozing through fractures in the ice crust. These geological timekeepers could be recycling Titan's chemistry over millennia, creating temporary warm pockets where reactions impossible in the Moon's frigid surface might flicker to life. If Dragonfly catches one of these regions mid-activation, it could witness alien chemistry in action. The rotorcraft's design is as ingenious as its targets. Titan's thick atmosphere, 4 times denser than Earth's, makes flying easier than on Mars, while its low gravity means Dragonfly can carry a full science lab between hops. Its neutron spectrometer will sniff out subsurface hydrogen, hinting at buried liquid water or organic reservoirs. A mass spectrometer will dissect atmospheric gases, hunting for isotopes that betray ongoing biological or geological activity. Every data point builds toward answering one haunting question: is Titan merely a frozen archive of life's ingredients, or could something be actively rearranging them? The implications ripple far beyond one moon. If Dragonfly finds molecules assembled in ways that defy random chemistry, chains of carbon with purposeful structures, or chiral imbalances favoring one molecular orientation, it could mean Titan's environment is nudging matter toward complexity. Maybe not life as we know it, but a proof of concept that the universe leans toward organization even in the most unexpected places. And if cryoval Konos are indeed refreshing the surface with organics, Titan becomes more than a time capsule. It's a dynamic factory, still churning out the raw materials for life billions of years after its formation. Dragonfly's greatest gift might be teaching us how broad the definition of habitable can stretch. A world with methane monsoons and ethane lakes shouldn't be a candidate for biology, yet here we are, betting billions on its potential. Whether it finds hints of life or simply a laboratory of cosmic chemistry, one thing's certain: Titan refuses to be pigeonholed. It's a reminder that the universe's creativity dwarfs our imagination, and sometimes you need a helicopter to chase the truth. TRAPPIST-1 sounds like something from a sci-fi novel, a star just 1/10 the size of our sun, burning so faintly it would appear only slightly brighter than a full moon from the surface of its planet. Yet this cosmic underdog hosts one of the most tantalizing planetary systems we've ever discovered. 7 Earth-sized worlds crammed so close together that standing on one would reveal neighboring planets looming larger in the sky than our moon. 3 of them, TRAPPIST-1e, F, and G, sit squarely in the star's habitable zone, where temperatures might allow liquid water to pool. But the real showstopper here is TRAPPIST-1e, a rocky world with a name straight out of a futuristic transit map and a backstory that could rewrite the rules of where life might thrive. Initial observations showed TRAPPIST-1e basking in just the right amount of starlight to maintain Earth-like temperatures, if it has an atmosphere to trap that heat. That's where the James Webb Space Telescope enters the scene. Recent spectroscopic studies have hunted for chemical fingerprints in the planet's air, searching for molecules like carbon dioxide, methane, or ozone that could hint at geological or even biological activity. Early data suggests this world might indeed cling to a wispy atmosphere, though whether it's a suffocating blanket of Venus-like gases or something more Earth-like remains unclear. But there's a catch actually, several. TRAPPIST-1's planets are likely tidally locked, meaning one side perpetually faces the star in scorching daylight while the other languishes in eternal night. On paper, this creates a hellish scenario, a planet split between a molten hemisphere and a frozen wasteland. Yet models suggest atmospheric currents could distribute heat, creating a narrow twilight belt where liquid water and life might persist. Imagine a world where civilization huddles along the Terminator line, balancing between fire and ice. Then there's the star itself. Ultra-cool dwarfs like TRAPPIST-1 are notorious for violent flares, capable of stripping atmospheres away over time. Some studies estimate these eruptions could bombard nearby planets with radiation doses thousands of times stronger than anything Earth experiences, but life is stubborn. Deep underground or shielded by thick ice, organisms could endure just as Earth's extremophiles do in radioactive environments like Chernobyl's reactor core. The beauty of this system lies in its contradictions. Planets so close they're practically siblings, yet each potentially sculpted by wildly different forces. TRAPPIST-1e might be a waterlogged oasis or a desiccated husk. We won't know until Webb or future telescopes deliver more clues, but every new data point proves one thing. Even in the quietest corners of the galaxy, the universe keeps dealing hands that defy our expectations. And this time it dealt 7. The James Webb Space Telescope is rewriting the rules of atmospheric detective work, especially for those tantalizing TRAPPIST-1 planets. When it turns its gold-plated eye toward TRAPPIST-1e, it's not just looking for oxygen, it's hunting for a cosmic balancing act. Oxygen alone would raise eyebrows but not guarantee life. Here's why. On a planet bombarded by ultraviolet light from its red dwarf star, water molecules high in the atmosphere can split apart through photolysis, releasing oxygen as a byproduct. It's a natural process we've seen on Europa and Ganymede worlds where oxygen exists without a single microbe to breathe it. But add methane to the mix and the story changes completely. These two gases are like matter and antimatter in atmospheric terms. They react rapidly to form carbon dioxide and water. If JWST spots them coexisting in TRAPPIST-1e's air, it suggests something is continuously replenishing both. On Earth, that something is life, plants pumping out oxygen while microbes and animals exhale methane. An abiotic world would struggle to maintain this delicate equilibrium unless it had exotic geology, like serpentinization reactions churning out methane while ultraviolet light generates oxygen. That's why astronomers call oxygen and methane together a biosignature pair. It's less about the ingredients and more about the persistence of their unlikely partnership. Now compare this to JWST observations of Proxima Centauri b, another rocky world in its star's habitable zone. There, tentative oxygen detections were complicated by the planet's extreme stellar flares, which can rip apart molecules faster than they accumulate. TRAPPIST-1e offers a cleaner test case. Its star is calmer, and with 7 planets transiting regularly, JWST can cross-check atmospheric data across the entire system. If only the habitable zone worlds show this chemical duet, the case for biology strengthens dramatically, yet the universe loves throwing curveballs. Imagine TRAPPIST-1e has vast shallow oceans where sunlight splits water vapor, while underground volcanoes seep methane through geothermal vents. That could mimic life's signature without any biology involved. Or perhaps the planet is a frozen snowball with oxygen trapped in surface ice, slowly released by meteorite impacts while methane bubbles up from deep reservoirs. JWST's job is to weigh these scenarios by measuring isotope ratios like oxygen 18 to oxygen 16, which tend to skew distinctly when life is involved. The real magic lies in the details. A biosignature wouldn't just shout oxygen and methane, it would whisper in molecular fine print. Organic molecules with recurring carbon chains or methane depleted in heavy carbon isotopes could tip the scales. Even the daily and seasonal fluctuations in these gases might betray life's rhythms. A living world breathes, pulses, and leaves traces in its atmospheric heartbeat. TRAPPIST-1e is more than a target, it's a laboratory for redefining how we recognize life from light years away. Every photon JWST captures carries fingerprints of a world that could be teaching us the most profound lesson of all. That life isn't an earthly accident, but a cosmic inevitability with infinite disguises. K2-18b shatters every expectation we had about where life might exist. This mini Neptune, over twice Earth's size and 8 times as massive, orbits a cool dwarf star 110 light-years away, and recent James Webb observations have detected something baffling in its thick hydrogen-rich atmosphere. Dimethyl sulfide, a molecule that on Earth is exclusively produced by living organisms. Plankton in our oceans release it as they photosynthesize, creating that distinctive sea air smell. Finding it floating above an alien world is like catching a whiff of ocean breeze from another solar system. But K2-18b is no Earth twin. Its hydrogen envelope stretches hundreds of miles thick, crushing the surface under pressures that would flatten submarines. Until recently, astronomers dismissed such worlds as sterile gas balls until the Hycean planet hypothesis emerged. These theorized worlds could have global oceans buried beneath their hydrogen atmospheres, kept liquid by immense pressure rather than sunlight. Picture an abyss where the sky weighs down like 1,000 oceans, yet microbial life thrives near hydrothermal vents, releasing gases that percolate up through the crushing layers. The catch: we've never seen a confirmed Hycean world before. K2-18b's DMS detection could be our first clue, or it could reveal gaps in our understanding of alien chemistry. Some models suggest that under extreme pressures, carbon and hydrogen might rearrange into DMS without biology's help. The planet's scorching temperatures around -100 degrees Fahrenheit at the ocean's theoretical surface add another wrinkle. Could Earth-like microbes survive in such frozen depths? Or would life here require entirely new biochemistries, perhaps using liquid hydrocarbons as solvents instead of water? Webb's data paints a tantalizing but ambiguous picture. Alongside DMS, the telescope spotted carbon dioxide and methane, exactly the cocktail you'd expect if biological processes were churning beneath that hydrogen shroud. But the same mix could also stem from geothermal activity cooking the planet's rocky core. The key lies in the ratios. Life tends to be messy, leaving uneven distributions of isotopes and byproducts. If future observations show DMS piling up in specific atmospheric layers or fluctuating with seasons, that skews the odds toward biology. Here's what makes K2-18b revolutionary. It forces us to expand the habitable zone concept. Traditional definitions focus on rocky planets with Earth-like atmospheres, but Hycean worlds could maintain liquid oceans far beyond those limits, powered by internal heat or tidal friction. Suddenly, hundreds of mini Neptunes in our galaxy's databases become candidates for subsurface life. Imagine oceans wrapped in eternal twilight, where the pressure is so intense water exists as a supercritical fluid, blurring the line between liquid and gas. Organisms here might harvest energy from chemical gradients near volcanic vents, their metabolism slowed but never stopped by the cold. The debate isn't just academic, it's shaping future missions. Proposed spacecraft like the Habitable Worlds Observatory would analyze K2-18b's atmospheric chemistry in unprecedented detail, hunting for other biomarkers like carbonyl sulfide or methyl chloride. Even the DMS signal's strength matters. Earth's plankton produce millions of tons annually. A weaker detection might suggest isolated pockets of life rather than a global biosphere. Every new data point pulls us deeper into the mystery of whether we're seeing a cosmic fluke or the first hints of a galactic oceanography. K2-18b challenges us to think beyond terrestrial paradigms. If life can stake a claim in the crushing depths of a Hycean world, then the universe's hospitality may stretch far beyond what we've dared imagine. Whether that DMS signal ultimately traces to alien plankton or exotic geology, one truth remains: the rules of the game just got rewritten. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: Oumuamua, the first known visitor from interstellar space. This strange object wasn't just notable for its origins. It behaved unlike any comet or asteroid we'd seen before. Tumbling end over end, its elongated shape resembling a cosmic cigar, Oumuamua accelerated as it moved away from the sun, an action that sent shockwaves through the scientific community. Comets typically accelerate due to outgassing, the release of heated gases as sunlight vaporizes their icy surfaces. But Oumuamua left no visible trail of gas or dust. So what was pushing it? Theories exploded faster than a supernova. Some suggested hydrogen outgassing, a process where sunlight vaporizes frozen hydrogen trapped in the object's interior, creating an invisible propellant. Others proposed tidal forces or solar radiation pressure, though calculations showed these were too weak to explain the anomaly. Then came the most provocative idea: Harvard astrophysicist Avi Loeb's hypothesis that Oumuamua might be artificial, a light sail or debris from an alien civilization, drifting through the cosmos like a message in a bottle. The media frenzy was instantaneous, but the scientific pushback was equally fierce. Critics pointed out that extraordinary claims require extraordinary evidence, and no radio signals or other technosignatures were detected. Yet Loeb countered with a compelling argument: why dismiss the possibility outright when nature struggles to explain the full picture? The debate forced astronomers to confront gaps in our understanding. Interstellar objects might follow rules we haven't yet deciphered. Oumuamua's dry, rocky surface and lack of a visible coma challenged traditional comet models, while its bizarre shape, estimated to be 10 times longer than it was wide, hinted at formation processes unlike anything in our solar system. Was it a shard from a shattered planet, a bizarre byproduct of molecular cloud collapse? Every explanation raised new questions. Now the race is on to prepare for the next Oumuamua. The European Space Agency's Comet Interceptor mission, launching in 2029, will lurk at a gravitational sweet spot, ready to chase down any future interstellar intruder. Meanwhile, projects like Lyra, a concept for a spacecraft that could rendezvous with Oumuamua-like objects, are pushing propulsion technology to its limits. These missions aim to settle the debate with hard data, capturing close-up images and chemical readings that could reveal whether Oumuamua was a cosmic oddball or a signpost to something far more profound. The legacy of this interstellar vagabond isn't just about solving a single mystery, it's about humility. Oumuamua reminded us that the universe is brimming with phenomena we haven't begun to categorize. Whether natural or otherwise, its fleeting visit was a wake-up call, a glimpse into the vast, uncharted diversity of objects sailing the galactic seas. And the next one might already be on its way. Deep in the cosmic static, astronomers caught something that shouldn't exist, a fast radio burst repeating on a schedule. FRB 121102, a burst of energy so powerful it outshines entire galaxies for milliseconds, wasn't just flaring randomly. In 2020, researchers noticed its eruptions followed a precise 157-day cycle, active for 90 days, silent for 67, like clockwork. This wasn't just cosmic noise, it was a rhythm, and rhythms in nature usually mean something spinning, orbiting, or dare we say counting. The leading theory points to a wildly exotic neutron star. Picture a city-sized magnetar, a stellar corpse with a magnetic field so strong it could strip the iron from your blood from 1,000 miles away. As it wobbles through space, a phenomenon called precession, its jets of radiation might sweep across Earth like a lighthouse beam, explaining the cyclical burst. But there's a plot twist. No known neutron star precession matches this exact timetable. The math leaves gaps, and gaps invite speculation. Could we be seeing the decay of an unstable orbit, or perhaps something even stranger, like a neutron star tangled in the gravitational web of a black hole companion? Then there's the elephant in the universe. Repeating patterns, especially those with mathematical consistency, are what SETI scientists dream of. The Breakthrough Listen project has been dissecting these bursts with AI, hunting for embedded structures or numerical sequences that might hint at encoding. So far, no luck, but the sheer regularity of FRB 121102 raises eyebrows. Natural astrophysical processes rarely keep time this precisely without a visible mechanism. It's the difference between hearing a tree fall in the forest and hearing it fall every Tuesday at 3 p.m. The implications ripple far beyond one burst. If neutron stars can produce cycles this clean, it reshapes our understanding of their physics. If they can't, we're left with a tantalizing void where explanations should be. Future telescopes like the Square Kilometre Array aim to catch these bursts mid-eruption, pinpointing their home galaxies with unprecedented precision. Each new detection is a breadcrumb not just toward solving an astrophysical puzzle, but toward answering the haunting question of whether patterns this deliberate could ever be more than celestial coincidence. The universe, it seems, loves a good mystery, and this one's ticking. In 2020, astronomers with the Breakthrough Listen project picked up something peculiar from Proxima Centauri, a narrowband radio signal at 982 MHz, dubbed BLC-1. This wasn't just random cosmic noise. The signal had a telltale drift, subtly shifting in frequency over time, almost as if coming from a moving source. On Earth, that's exactly how our own satellites and spacecraft appear when their signals Doppler shift due to motion. For a brief, electrifying moment, the possibility hung in the air. Had we just intercepted a transmission from our nearest stellar neighbor? The signal's characteristics made it a standout candidate for technosignature hunting. Unlike the broad, messy emissions from natural astrophysical processes, BLC-1 was laser-focused in frequency, the kind of precision typically associated with artificial transmitters. Even more intriguing, it originated from the direction of Proxima Centauri b, a rocky exoplanet nestled in its star's habitable zone. The ingredients were all there, a potentially life-friendly world just 4.2 light-years away, and now a signal that mimicked human-made technology. But the cosmos loves a good plot twist. Further analysis revealed interference might be the culprit. The signal's frequency coincided with known terrestrial radio bands used by satellites and surface transmitters. Worse, subsequent observations failed to redetect it, a red flag in the search for extraterrestrial intelligence where genuine signals should persist. Some researchers suggested the culprit could be a passing satellite or even a malfunctioning microwave oven on Earth, its emissions bouncing off structures or the ground in just the right way to mimic an interstellar broadcast. Yet BLC-1's legacy isn't about disappointment, it's about validation. The fact that we detected, scrutinized, and debated this signal shows how far technosignature research has come. A century ago, such precision monitoring would have been impossible. Today, projects like Breakthrough Listen can sift through millions of radio channels simultaneously, filtering out earthly interference with increasingly sophisticated algorithms. The episode also underscored a critical lesson: persistence is key. One-off signals, no matter how tantalizing, need repeatable verification. That's why astronomers continue to monitor Proxima Centauri and other nearby stars, knowing the next signal might not be so easily dismissed. The search has only intensified since 2020. New telescopes like the Square Kilometre Array promise unprecedented sensitivity, capable of detecting a cell phone signal from a nearby star. Meanwhile, researchers are expanding beyond radio, hunting for laser pulses, atmospheric pollution, or even megastructures around distant suns. Proxima's mysterious signal may have faded, but it left behind a roadmap, a reminder that the universe is vast and the next great discovery might be just one scan away. One summer night in 1977, an Ohio State University radio telescope captured a signal so extraordinary it was circled in red ink with a single word scribbled beside it: "Wow." For 72 blistering seconds, this burst of radiation blazed across the hydrogen line, the specific frequency at 1420 MHz where scientists had long theorized extraterrestrials might transmit. The signal's intensity peaked 30 times above background noise, matching predicted profiles for interstellar communication. Then, just as suddenly as it appeared, it vanished, never to be heard again despite decades of frantic searching. What made the WOW signal so electrifying wasn't just its strength, it was its specificity. The hydrogen line is cosmic radio's quietest channel, where the noise of the universe drops to a whisper. Any civilization broadcasting there would know their message could travel farthest with the least interference. The signal's narrow bandwidth, less than 10 kHz, ruled out most natural phenomena which tend to scatter across frequencies. And its 72-second duration, that's exactly how long the Big Ear telescope's fixed antenna would see a point source as Earth rotation swept it into view. The pieces fit together like a puzzle designed to catch our attention. Yet the mystery only deepens when you ask why we've never caught it again. Some argue it could have been a one-time event, an alien beacon momentarily aimed our way, or a rogue satellite reflecting terrestrial transmissions in a freak alignment. Others point to the comet theory, suggesting hydrogen clouds from passing comets 266P/Christensen and 335P/Gibbs might have emitted resonant bursts. But detailed orbital reconstructions show neither comet was in the right constellation Sagittarius when the signal arrived. Modern tools are rewriting the playbook for solving this enigma. The upcoming Square Kilometre Array, with millions of antennas spanning 2 continents, will monitor the WOW signal's patch of sky with sensitivity 100 times greater than the Big Ears. Unlike its predecessor, SKA will track multiple frequencies simultaneously, eliminating the agonizing wait between scans that might have missed follow-up transmissions. Machine learning algorithms can now sift through radio noise in real time, flagging patterns human operators might overlook. Perhaps the most tantalizing possibility isn't finding a repeat of the WOW signal, but uncovering something even stranger. New analysis suggests the original signal might have carried subtle modulations, like amplitude dips encoding information. Advanced software could decode these patterns if only we had more data. Meanwhile, Breakthrough Listen's latest archives contain several uncanny near-matches brief, strong signals from nearby stars that vanished before verification. Could these be cosmic echoes of the same phenomenon? The WOW signal endures not because it gave us answers, but because it taught us how to listen. Every failed follow-up, every debated theory, sharpens our tools for the next cosmic whisper. Whether it was a fleeting hello or a cosmic mirage, one truth remains: the universe is vast enough to hide countless wonders, and sometimes, just sometimes, it winks at us. Tabby's star, officially known as KIC 8462852, should have been just another flicker in Kepler's data logs. Instead, it became one of the most debated cosmic anomalies of the decade. Between 2009 and 2013, this distant sun, roughly 1,500 light-years away, exhibited wild, unpredictable dips in brightness, sometimes losing up to 22% of its light for days at a time. No known planet, comet swarm, or stellar phenomenon could explain such extreme fluctuations. The internet erupted with speculation. Were we witnessing a Dyson swarm, a colossal megastructure built by an advanced civilization to harvest their star's energy? For a brief moment, science fiction seemed to bleed into reality. The idea wasn't entirely far-fetched. Physicist Freeman Dyson had theorized in the 1960s that a sufficiently advanced society might construct vast solar collectors around their star, capturing its power and radiating waste heat as infrared light. Tabby's star's bizarre dimming patterns fit the profile, especially when initial studies ruled out more mundane explanations, but the cosmos rarely serves up easy answers. Over years of scrutiny, a dustier truth emerged. Observations from the Hubble and Keck telescopes revealed the star's light was being polarized, a telltale sign of microscopic particles scattering its rays. The leading theory now suggests a massive, uneven dust cloud, perhaps debris from a shattered planet or a swarm of comets, is responsible for the erratic dimming. Yet the mystery hasn't fully closed. Some dips remain stubbornly asymmetrical, lacking the clean, U-shaped profile typical of dust transits. Others occur at irregular intervals, defying the predictable rhythms of orbiting debris. That's where the James Webb Space Telescope enters the picture. With its unmatched infrared sensitivity, Webb could finally settle the debate by hunting for two critical clues: the thermal fingerprint of dust expected to glow at specific mid-infrared wavelengths, or, more tantalizingly, the diffuse heat signature of artificial structures. A Dyson swarm would radiate at temperatures consistent with solar-powered machinery, creating an excess of infrared light that no natural dust cloud could mimic. Even if Webb confirms the dust hypothesis, Tabby's star has already reshaped how we approach cosmic anomalies. It taught astronomers to withhold snap judgments while keeping imaginations alive, because sometimes the weirdest data leads to the most profound questions. Whether the answer is dust or something far stranger, this star reminds us that the universe still holds puzzles we've only begun to decode. Pulsar PSRB 1257 plus 12 shouldn't have planets at all. This spinning stellar corpse, a neutron star whirling at over 6,000 revolutions per minute, was once a massive sun that exploded in a supernova, an event so violent it should have vaporized any nearby worlds. Yet in the early 1990s, astronomers detected not just one, but three tiny objects circling this cosmic wreckage. These weren't ordinary planets. Dubbed the pulsar planets, they were survivors of an apocalypse, likely the shattered cores of former gas giants, forged into ultra-dense orbs under conditions that defy imagination. The most bizarre of these worlds might have a secret locked beneath its surface, a diamond crust hundreds of miles thick. The violent death of their parent star would have flooded the remnants with carbon, compressed under such extreme pressure that it crystallized into a lattice of diamond. On Earth, carbon-based life thrives in every corner, from the depths of oil wells to the icy tundras. But on these pulsar planets, life, if it exists, would play by entirely different rules. Imagine organisms with cellular structures built from diamond-like carbon frameworks, their metabolisms powered not by sunlight, but by the relentless particle winds streaming from the pulsar itself. Radiation that would kill terrestrial life in seconds might be their lifeblood, feeding exotic chemistries we've yet to conceive. The contrasts with Earth are staggering. Our biology relies on silicon-based compounds and liquid water, with DNA as its blueprint. On a pulsar planet, the building blocks might be graphene sheets or carbon nanotubes, with liquid methane or even supercritical hydrogen as solvents. The crushing gravity, hundreds of times stronger than Earth's, would demand life forms with structures more like crystalline sculptures than fleshy bodies. Some theories suggest such organisms could resemble mineral-based extremophiles, their life cycles operating at a glacial pace to conserve energy in a world where a single misstep could mean annihilation. Yet the most tantalizing clue lies in the pulsar's steady rhythm. Just as Earth's rotation gives us day and night, the pulsar's beams could create cycles of radiation and relative calm, offering niches where life might eke out an existence. The energy density is absurdly high enough that even a minuscule capture efficiency could power complex systems. Microbes analogous to Earth's radiotrophic fungi, which thrive in Chernobyl's reactors, might flourish here, absorbing gamma rays the way plants absorb photons. Astrobiologists call these second genesis worlds, places where life, if it exists, would have arisen from scratch after the supernova, independent of anything that came before. That makes them the ultimate test of life's universality. Whether they host diamond-encrusted extremophiles or remain sterile curiosities, pulsar planets force us to stretch the definition of habitable to its breaking point. They're reminders that the cosmos doesn't play favorites, it simply offers raw materials and waits to see what sticks. And sometimes, against all odds, what sticks is stranger than fiction. Rising from the heart of the Milky Way like two colossal hourglasses, the Fermi bubbles stretch 50,000 light-years, nearly half the diameter of our entire galaxy. These titanic structures, discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, glow with high-energy radiation, their edges sharply defined against the darkness of intergalactic space. At their base lies Sagittarius, a star, the supermassive black hole anchoring our galaxy, whose violent past might hold the key to this cosmic spectacle. Most astrophysicists agree the bubbles are scars from an ancient eruption, a black hole belch of unimaginable scale. When Sagittarius, a star, feasted on a passing gas cloud or star millions of years ago, it could have unleashed twin jets of plasma at near light speeds, punching through the galactic disk and inflating these magnetized balloons. Supporting this, the bubble's gamma-ray emission matches models of accelerated particles interacting with interstellar gas. But there's a wrinkle: some energy signatures inside the bubbles don't quite fit. Certain regions show unexpectedly uniform particle distributions, as if something sculpted them deliberately. That's where the fringe theories ignite. A minority hypothesis suggests the bubbles might not be natural at all, but relics of a Type II civilization's energy project, a Kardashev-scale power collector, or even a galactic communication beacon. The symmetry is striking: two nearly identical lobes perfectly aligned with the galactic core. While Occam's razor favors the black hole explanation, the sheer scale of the structures invites speculation. Could an advanced culture have harnessed their black hole's energy, leaving behind gamma-ray breadcrumbs? Enter the Cherenkov telescope array, poised to revolutionize this debate. Slated for completion in 2030, this next-generation observatory will map the bubble's substructure in unprecedented detail, hunting for telltale patterns in particle acceleration. If the energy distribution follows chaotic, natural shock fronts, the black hole theory wins. But if it reveals geometric arrangements, concentric rings, or unnaturally straight filaments, the conversation shifts dramatically. Beyond the mystery lies a deeper lesson. Whether natural or artificial, the Fermi bubbles remind us that galaxies aren't static paintings but dynamic engines, capable of violence and beauty on scales we're only beginning to fathom. Their very existence proves that even our quiet corner of the cosmos has a dramatic past, and perhaps, if we're bold enough to consider it, a stranger future. The Fermi paradox has haunted scientists for decades. If the universe is so vast and ancient, why does it feel so empty? With recent discoveries like the organic-rich plumes of Enceladus and the methane-drenched skies of exoplanet K218b, the paradox isn't just deepening, it's mutating. We now know the building blocks of life are scattered across the cosmos like cosmic confetti, from the icy geysers of Europa to the hydrocarbon lakes of Titan. The problem isn't finding places where life could exist, it's figuring out why we haven't found any that do. One unsettling explanation: life might be everywhere, but intelligence could be the universe's rarest fluke. Think of Earth's 4.5 billion year history. Microbes dominated for 3 billion of those years before multicellular life even got a foothold. Then consider how many near extinctions it took to shape human intelligence: asteroid impacts, ice ages, volcanic winters. If most life gets stuck at the bacterial stage or gets wiped out by cosmic disasters before developing technology, the silence starts to make sense. This idea, the great filter, suggests something in evolution's chain is almost impossible to clear, and the terrifying question remains: is the filter behind us meaning we've beaten the odds, or ahead of us waiting to wipe us out? Yet there's a twist that's equally mind-bending. The zoo hypothesis flips the script, proposing advanced civilizations might be watching us like a galactic nature preserve, intentionally avoiding contact until we're ready. It sounds like sci-fi until you consider how carefully we shield uncontacted tribes on Earth. Or maybe the truth is darker. What if interstellar societies do communicate, but through channels we're too primitive to detect? Imagine ants in a forest, oblivious to the Wi-Fi signals buzzing overhead. Our radio telescopes might be the equivalent of smoke signals in an age of quantum entanglement. Recent discoveries throw gasoline on this debate. The fact that we found oceans inside moons and atmospheres on worlds light years away means habitable real estate is abundant, yet we found zero technosignatures. Not a single Dyson swarm, no galaxy-spanning megastructures. Either intelligence is vanishingly rare, or it's hiding in ways we can't fathom. The James Webb Telescope's atmospheric analyzers might soon tip the scales. If it keeps finding planets rich in oxygen and methane but no signs of industry, the great filter gains credence. But if it spots a world with freon or nuclear byproduct chemicals with no natural explanation, the zoo hypothesis starts looking less like fantasy and more like a survival strategy. The paradox isn't just a puzzle, it's a mirror. Every new discovery forces us to confront how little we know, not just about the cosmos, but about our own future. Are we the universe's first sparks of consciousness, or just late to a party that's already ended? The answer might lie buried in the ice of Enceladus or in the silent glow of a distant star. Until then, the silence remains our greatest teacher. The Murchison meteorite didn't just fall to Earth in 1969. It crashed into our understanding of life's origins like a cosmic grenade. This charred space rock found in Australia carried something revolutionary locked inside its ancient grains, a smorgasbord of organic molecules from amino acids to ribose sugars, the very building blocks of proteins and RNA. But here's what flips the script: these weren't just random chemicals. They mirrored the structures life uses on Earth, right down to left-handed amino acids, a bias so specific it screams biology. The discovery ignited a firestorm. Did life's ingredients hitchhike across the galaxy to jumpstart our planet, or was this just a fortunate cosmic coincidence? Laboratory experiments have since turned up the heat on this debate. When scientists simulate deep space conditions bombarding icy dust grains with ultraviolet radiation or cosmic rays, they watch in real time as complex organics like uracil and cytosine, key components of DNA and RNA, emerge from the chaos. It turns out the void between stars isn't empty. It's a sprawling chemical factory where freezing temperatures and relentless radiation forge molecules far more intricate than we once thought possible. The implications are staggering. If probiotic chemistry can cook up life's essentials in the harshest environments imaginable, then the raw materials for biology might be as common as stardust. Yet the plot thickens when you examine Murchison's extrasolar passport. Isotopic analysis revealed its sugars and amino acids carried heavy carbon isotopes, a signature proving they formed in cold interstellar clouds long before our solar system existed. These molecules weren't just passengers on a rock, they were interstellar travelers, surviving billions of years in deep freeze until landing in our backyard. Suddenly, panspermia, the idea that life's seeds spread between worlds, doesn't sound so far-fetched. Imagine comets as cosmic FedEx trucks, delivering organic parcels to young planets like Earth during the chaotic early days of the solar system. But skeptics raise a valid counterpoint. Finding life's Lego bricks isn't the same as finding assembled blueprints. Just because space can produce amino acids doesn't mean it can string them into proteins or encode genetic information. The leap from chemistry to biology remains vast, and no meteorite has yet offered proof that this gap was bridged beyond Earth. Still, the Murchison meteorite forces us to confront an exhilarating possibility: that life's origins might not be a local story, but a galactic epic written in atoms older than the Sun. Every speck of interstellar dust could be a page in that manuscript, waiting to reveal how ordinary chemistry becomes extraordinary biology. The search for answers now stretches from lab benches to asteroid missions. Japan's Hayabusa 2 and NASA OSIRIS-REx have already returned fresh samples from carbon-rich asteroids, their cargo likely packed with even more pristine organics than Murchison. As we dissect these time capsules, we're not just studying rocks, we're reading a recipe book the universe has been compiling for billions of years. And if even one of its pages holds instructions for life, then we might all be descendants of stardust with a very long commute. The cosmos might be quieter than we think for a reason, and it's not because we're alone. The dark forest hypothesis paints a universe far more sinister than Star Trek's diplomatic federations or Contact's hopeful transmissions. Imagine a galactic game of hide and seek where every civilization stays silent, terrified of attracting the attention of something far worse. The logic is brutal. Any society advanced enough to broadcast its location risks annihilation by hostile superpredators scanning the skies for threats. In this scenario, staying invisible isn't just prudent, it's the only way to survive. This isn't just science fiction. The theory takes cues from humanity's own history: colonizers wiping out isolated tribes, or Cold War powers hiding nuclear silos to avoid first strikes. On a cosmic scale, the stakes are infinitely higher. A single misstep, one careless radio transmission, could draw the gaze of a civilization with technology beyond comprehension. That might explain why we've never picked up unambiguous signals despite decades of listening. The universe isn't empty, it's full of civilizations holding their breath. Now re-examine anomalies like Oumuamua or those repeating fast radio bursts through this lens. Could Oumuamua's strange acceleration have been a disguised probe, scanning our system while staying deliberately inert? Some FRBs pulse with patterns so precise they mimic radar sweeps, perfect for mapping galaxies without revealing the sender's location. Even the WOW signal's one-off nature fits, a momentary slip quickly silenced. The dark forest doesn't just explain the silence, it turns every unexplained cosmic flicker into a potential warning. Yet not everyone buys into this cosmic paranoia. METI International, led by Douglas Vakoc, actively broadcasts messages to nearby stars, arguing that hiding guarantees loneliness. Their reasoning: a civilization capable of interstellar aggression would already know we're here from our TV and radio leakage. If they wanted us gone, we'd be gone. Instead, they might be waiting for us to pass a technological threshold proving we're worth talking to. The debate cuts to the core of how we view intelligence. Is the universe a battlefield where only the paranoid survive, or a classroom where curiosity is rewarded? Until we have proof, the dark forest remains a shadow lurking at the edge of every SETI calculation. A reminder that the scariest answer to Fermi's paradox might not be that we're alone, but that we're not. And everyone else is too afraid to say hello. Kepler 1649c isn't just another exoplanet, it's the cosmic equivalent of finding your doppelganger in a crowd of billions. Nestled 300 light-years away in the constellation Cygnus, This rocky world is almost a perfect Earth twin. From its 1.06 Earth radii to its balmy estimated surface temperature hovering around -40 degrees Fahrenheit cold, but within the realm of human survival with the right technology. What really sets it apart is that staggering Earth similarity index of 0.89, a hair's breadth from our own planet's score of 1. For context, Mars clocks in at a measly 0.64. Kepler 1649c doesn't just orbit its star's habitable zone. It lounges there, soaking in just 75% of the sunlight Earth receives, making it a prime candidate for liquid water. But let's not sugarcoat the challenges. Its sun, a red dwarf called Kepler 1649, is the kind of star that brings both gifts and curses. These diminutive stars burn so slowly they'll outlive the universe's current age by trillions of years, offering life an almost endless runway to evolve. Yet they're also infamous for their tantrums, violent UV flares that can strip atmospheres and bathe surfaces in radiation. Early models suggested these eruptions might render any nearby planet sterile, but newer research paints a more nuanced picture. A robust atmosphere or a planetary magnetic field could act as a shield, and there's even evidence that some extremophiles on Earth use UV radiation as an energy source. Life, if it's there, might have adapted to treat flares like a daily cup of cosmic coffee. The real excitement lies in what comes next. The James Webb Space Telescope has Kepler 1649c firmly in its crosshairs, ready to dissect its atmosphere for the faintest whispers of biology. Scientists are hunting for two game-changing signatures: carbon dioxide spikes that could hint at a geologically active world with volcanoes recycling gases, and something called the vegetation red edge. On Earth, plants reflect a unique infrared glow when chlorophyll absorbs sunlight, a fingerprint so distinct it's visible from space. Spotting a similar signal here wouldn't just suggest life, it would imply photosynthesis has taken root under an alien sun. Yet the most tantalizing possibility isn't just finding life, it's finding familiar life. If Kepler 1649c's atmosphere shows oxygen paired with methane or surface features that change with seasons, we'd be staring at a world where biology followed a playbook eerily like Earth's. That would force us to confront a profound idea, that the universe might have a favorite recipe for life, and we're just one iteration of it. Or, if the chemistry looks utterly alien, it could mean life is even more inventive than we've dared to dream. For now, Kepler 1649c hangs in the balance, a puzzle wrapped in starlight, daring us to look closer. Whether it's a sterile mirror or a thriving sibling, its very existence proves that Earth might not be the universe's only masterpiece. And with every scan, every flicker of data, we're not just studying a planet. We're testing whether life is a cosmic fluke or an inevitability written into the fabric of reality itself. Imagine a world where the night sky is dominated not by one sun, but by a swirling gas giant 30 times wider than Earth's moon, its bands of storm clouds painted in hues of crimson and gold. This isn't Jupiter, it's the hypothetical exomoon Kepler 1625b, a tantalizing blip in data from the Kepler Space Telescope that might be our first glimpse of a habitable moon beyond our solar system. Like Europa orbiting Jupiter, this distant moon could harbor a global ocean beneath an icy shell, kept liquid by the relentless gravitational kneading of its colossal parent planet. But here's the twist: where Europa's ocean is buried under miles of ice, Kepler 1625b might have tides so extreme they create subsurface geysers, launching plumes of water into space like cosmic fountains, giving us free samples of a potential alien biosphere. The physics at play here are nothing short of spellbinding. Gas giants like Kepler 1625b don't just passively host moons, they sculpt them. Tidal forces flex and heat their interiors, potentially creating hydrothermal vents on the ocean floor where life could thrive without sunlight. On Earth, such vents host lush ecosystems of tube worms and blind shrimp, all fueled by chemical energy rather than photosynthesis. Now picture that same scenario on an exomoon, but with one critical difference. The energy source isn't just geothermal, it's amplified by the gravitational dance between the Moon, its planet, and neighboring satellites. This trio could generate tidal heating so intense it keeps the ocean liquid for billions of years, far beyond the star's traditional habitable zone. Detecting these hidden worlds is like playing cosmic Sherlock Holmes. Exomoons don't just dim their star's light like planets do. They leave subtler clues. As a moon orbits its gas giant, their combined gravity creates a wobble in the star's motion, a telltale sway that advanced telescopes like the upcoming European Extremely Large Telescope could spot. There's also the transit timing variation method, where a moon's gravity slightly delays or accelerates its planet's transit across the star, like a hidden puppeteer tugging on strings. Kepler 1625b's potential discovery hinged on this very phenomenon, a mysterious dip in starlight that couldn't be explained by the gas giant alone. But the real magic lies in imagining what these moon-bound oceans could hold. Europa's extreme conditions have already rewritten our understanding of where life can exist. What if Kepler 1625b's tides generate even more energy, creating underwater currents that distribute nutrients globally? Or what if its ice shell is thinner, allowing photosynthesis at shallow depths beneath cracks filled with cryovolcanic slush? The possibilities spiral further when you consider the Moon's atmosphere. Tides might squeeze out gases from the interior, creating a thin envelope of water vapor or even oxygen, detectable by next-generation spectrographs. This isn't just about finding a new class of habitable worlds. Exomoons like Kepler 1625b could outnumber Earth like planets 10 to 1 in our galaxy. Gas giants are common, and many lurk in their stars' habitable zones, meaning their moons might be the true cradles of cosmic life. The search for these hidden oases is more than a scientific pursuit. It's a reimagining of where and how life might flourish. Every wobble in a star's motion, every anomalous flicker of light, could be a moon whispering its secrets across the void. Picture a planet untethered to any star, drifting through the void like a cosmic ghost. No sunrise, no seasons, just endless night stretching across millennia. These aren't the stuff of sci-fi. Astronomers now estimate our galaxy alone could harbor billions of these rogue worlds, flung from their parent systems by gravitational chaos or born in the frigid isolation of interstellar space. Unlike the familiar planets basking in starlight, these nomads wander the darkness, their surfaces frozen to near absolute zero. But here's the twist: beneath their icy crusts, some might be hiding secrets warmer and far stranger than we ever imagined. Take Earth's own deep biosphere as proof. Miles below our feet, in places where sunlight never penetrates, life thrives in the most unexpected ways. Microbes like Desulfurudes audaxviator survive solely on radioactive decay from rocks, metabolizing hydrogen and sulfur in a chemical dance that requires no organic food or oxygen. In South Africa's gold mines, scientists found entire ecosystems thriving 2 miles underground, sustained by geothermal heat and water trickling through ancient rock fractures. Now scale that up to a rogue planet. If a free-floating world retained even a fraction of its formation heat or hosted radioactive elements like uranium and thorium in its core, hydrothermal vents could churn away for eons in the abyss, creating pockets of liquid water and energy ripe for life. The real kicker: we've already spotted these cosmic drifters. Microlensing surveys, which detect planets by the way their gravity bends light from distant stars, have revealed tantalizing candidates. In 2020, a team analyzing data from Poland's optical gravitational lensing experiment estimated there could be 20 times more rogue planets than stars in the Milky Way. Some might even be warm enough to sport subsurface oceans, insulated by thick ice shells that trap geothermal heat like a thermos. Imagine Europa's hidden seas, but untethered from any solar system, a self-contained biosphere adrift in the galaxy. And then there's the wild card, tidal heating. Binary rogue planets, two worlds locked in mutual orbit, could squeeze each other's interiors through gravitational friction, generating enough warmth to keep subsurface water liquid even without a star. It's a scenario that turns conventional ideas of habitability upside down. Forget the Goldilocks zone. These worlds would carry their own heat source, turning the entire galaxy into a potential oasis for life. The implications are staggering. If even a fraction of rogue planets host subsurface life, the universe might be teeming with organisms that never see a sunrise, thriving in perpetual darkness. Future missions like NASA's Nancy Grace Roman Space Telescope, equipped to detect these lone wanderers through microlensing, could soon turn speculation into reality. Every rogue planet spotted isn't just a scientific curiosity. It's a reminder that life might be more resilient and more inventive than we ever dreamed. The cosmos doesn't need stars to cook up biology. Sometimes all it takes is a little heat from below and a lot of time. Deep in the swirling chaos of a young star system, half a light century from Earth, radio telescopes have spotted something extraordinary, a cloud of sugar molecules drifting through the void like cosmic candy. In 2012, the Atacama Large Millimeter Array locked onto the telltale fingerprint of glycolaldehyde, a simple sugar and a critical building block for RNA, swirling around the infant star era's 16293. This wasn't just a chemical curiosity, it was proof that the universe is prepping life's ingredients long before planets even form. Glycolaldehyde might sound like a lab reagent, but its role in the origins of life is nothing short of revolutionary. When combined with other molecules like formaldehyde, also found in stellar nurseries, it can undergo a series of reactions called the Formose process, churning out ribose sugars. Ribose is the backbone of RNA, the molecule many scientists believe bridged the gap between simple chemistry and biology on early Earth. Picture this: in the frigid clouds around protostars, icy dust grains act as microscopic labs where radiation cooks simple molecules into increasingly complex structures. These sugars don't just form randomly, they're products of a cosmic assembly line, with each step nudging matter closer to biology's doorstep. The real magic happens when these molecular Legos hitch a ride to planets. Comets, those dirty snowballs left over from solar system formation, are packed with organic compounds. When they slam into young worlds like Earth 4 billion years ago, they deliver more than water. They rain down sugars, amino acids, and other life-friendly molecules. Experiments at the University of Hawaii simulated this process, shooting artificial comets at targets mimicking primordial Earth. The impacts not only survived the collision but catalyzed new reactions, creating even more complex organics in the process. It's as if the universe designed comets as interstellar couriers, programmed to kickstart chemistry wherever they land, yet the story doesn't end there. Ulma later observations revealed glycolaldehyde in places even more unexpected, like the planet-forming disks around stars like TW Hydri, where fledgling worlds are actively assembling. This means sugars aren't rare cosmic accidents, they're inevitable byproducts of star formation woven into the fabric of planetary birth. The implications are staggering. If RNA's building blocks are this abundant, the leap from chemistry to biology might not be a fluke but a natural progression, written into the laws of physics and chemistry. What's truly humbling is the timeline. The glycolaldehyde swirling around era's 16293 predates our solar system by billions of years. Those same molecules could now be part of your DNA, their atoms forged in stellar nurseries before Earth existed. Every time you eat a spoonful of sugar, you're tasting a relic of cosmic history, one that might hold the secret to why life exists at all. For 60 years, we've been leaning into the cosmic static, ears straining for a whisper that never comes. The silence is deafening. Despite scanning thousands of stars across millions of frequencies with projects like SETI and Breakthrough Listen, the universe has responded with radio silence. No repeating patterns, no mathematical pulses, not even a stray transmission leaking from a distant civilization's equivalent of reality TV. This eerie absence has a name, the Great Silence, and it's forcing us to confront an uncomfortable truth. Maybe we've been searching all wrong. The problem starts with our assumptions. Human technology exploded with radio waves, so we naturally assumed advanced civilizations would broadcast similarly. But what if radio is just a fleeting phase in a civilization's development, a century-long blip before they switch to tighter, more efficient signals? Imagine an alien astronomer pointing their version of a telescope at Earth today. They'd catch fading echoes of I Love Lucy broadcasts from the 1950s, then nothing. Our modern fiber optic cables and encrypted digital signals are nearly invisible across interstellar distances. If extraterrestrials made the same leap, their signals might be as undetectable to us as a laser pointer in a solar flare. That's why researchers are pivoting to optical SETI scanning for pulsed laser signals instead of radio waves. A tightly focused laser could beam information with unimaginable efficiency, packing the power of a radio transmitter into a beam as narrow as a pencil. Harvard's Project LIGO has already scanned thousands of stars for nanosecond laser flashes, the kind an advanced civilization might use for high-bandwidth communication or even as a cosmic hello. Then there's the neutrino hypothesis, ghostly particles that slice through entire planets without slowing. A neutrino-based message wouldn't just be efficient, it'd be nearly impossible for natural phenomena to mimic. But the Great Silence isn't just about technology, it's about scale. The Milky Way alone spans 100,000 light-years, meaning even a signal traveling at light speed would take millennia to cross it. Civilizations might rise and fall before their signals reach a single neighbor. Add to that the mind-boggling timescales of cosmic evolution, and the odds of overlapping with another technological species become staggeringly slim. We're not just searching for aliens, we're searching for aliens who happen to be broadcasting in the same brief sliver of cosmic time. Perhaps the most humbling possibility is that we're not listening to the right kind of noise. Nature is anything but silent, fast radio bursts, pulsar pulses. Even the rhythmic dimming of stars could be cosmic billboards we're misreading as natural phenomena. The wow signal might have been our first and only clue, a fleeting moment when the universe's volume knob briefly turned up. Until we learn to decode the universe's full vocabulary, the Great Silence will persist, not as proof of emptiness, but as a testament to how much we still have to learn. The cosmos isn't ignoring us, we're just barely beginning to understand its language. What if the life we recognize is just one version of a story the universe tells repeatedly with infinite variations? The shadow biosphere hypothesis dares to suggest that Earth itself might harbor life forms so alien, they've eluded detection simply because we didn't know how to look. Imagine organisms not built on the familiar framework of carbon, water, and DNA, but on arsenic, silicon, or even solvents like ammonia, a hidden layer of biology operating under radically different rules. This isn't just speculation, it's a challenge to our very definition of life. The controversy erupted in 2010 with the discovery of a bacterium called G-Phage1 in California's Mono Lake, a body of water so alkaline and arsenic-rich it was long considered sterile. NASA scientists claimed this microbe didn't just survive in arsenic, it incorporated the toxic element into its DNA, replacing phosphorus in its backbone. Phosphorus is fundamental to all known life, essential for energy-carrying molecules like ATP and the structure of genetic material. If G-Phage1 truly swapped it for arsenic, it would rewrite biochemistry textbooks. The scientific community exploded with skepticism. Critics argued the bacteria might have been tolerating arsenic rather than relying on it, like a prisoner surviving on crumbs instead of proper meals. Subsequent studies failed to replicate the findings, leaving the claim in limbo. Yet the debate unlocked a profound question. If arsenic-based life exists, how would we even recognize it? Our tools are calibrated for carbon-based chemistry. PCR machines amplify DNA, spectrometers hunt for familiar organic signatures, and microscopes are tuned to recognize cellular structures we've seen before. A shadow biosphere, if it exists, might be invisible to these methods. It's like searching for a person in a crowded room using only a metal detector. You'll find keys and coins, but miss everyone else. This forces us to rethink extreme environments not as dead zones, but as potential hideouts for alternate life. Take Chile's Atacama Desert, where microbes survive by extracting moisture from rocks, or the boiling acid pools of Yellowstone, home to organisms that thrive where metal dissolves. If life can flourish there, why not in places with entirely different chemical foundations? Some researchers are now designing agnostic detection tools, sensors that look for patterns of complexity rather than specific molecules. These could spot life by its organized behavior, whether it's based on proteins or something entirely unknown. The implications stretch beyond Earth. If our planet hosts multiple, independent origins of life with distinct biochemistries, the universe is likely teeming with forms we've yet to imagine. Mars' perchlorate-rich soil or Titan's methane lakes might not be barren, just alien in ways our current probes can't fathom. The shadow biosphere isn't just a scientific frontier, it's a mirror held up to our assumptions. Every time we declare an environment lifeless, we might simply be confessing the limits of our imagination. So the next time you walk past a steaming volcanic vent or a sun-baked salt flat, consider this. You could be brushing shoulders with a second Genesis, a parallel biology quietly thriving in plain sight. The universe seldom settles for one solution when many are possible. The real question isn't whether shadow life exists, it's whether we're bold enough to redefine what life even means. James Lovelock's Gaia hypothesis shook the scientific world in the 1970s with its radical proposition that Earth isn't just a rock hosting life, but a dynamic superorganism where life and environment co-evolve in a self-regulating dance. From ocean algae seeding clouds to rainforests recycling water, our planet seems to play an active role in maintaining conditions suitable for biology. But what if this isn't unique to Earth? Imagine distant exoplanets where life, whether microbial or complex, subtly engineers its own atmosphere, leaving behind chemical fingerprints we could decode from light years away. The implications are staggering. We might not need to find radio towers or cities to prove a world is alive. Its air alone could be screaming with evidence. Take methane, a gas that's stubbornly unstable in most planetary atmospheres. On Earth, sunlight should break it down within a decade, yet it persists because life constantly replenishes it. Cows, swamps, and even termites churn out millions of tons annually. Now picture an exoplanet where methane appears in similarly improbable abundance, dancing in atmospheric models with no geological explanation. Volcanoes can produce methane, but not fast enough to sustain high concentrations without help. If we spotted such a world, especially one with oxygen coexisting, a combination that should combust into carbon dioxide without constant biological input, the case for a Gaian biosphere would be compelling. Oxygen offers an even more tantalizing clue. On Earth, cyanobacteria transformed our atmosphere 2.5 billion years ago during the Great Oxidation Event, flooding the skies with this reactive gas as a waste product of photosynthesis. But oxygen isn't just a byproduct, it's a planetary thermostat. As plants and algae bloom, they draw down carbon dioxide, cooling the climate. When temperatures drop, growth slows, allowing CO2 to rebound. It's a feedback loop so elegant it feels engineered, except no engineer is at the wheel. Life unconsciously regulates the very conditions it needs to survive. The James Webb Space Telescope is already hunting for these patterns in alien atmospheres. When it analyzed K218b, the so-called Hycean world, hints of dimethyl sulfide, a molecule only produced by Earth's marine plankton, sent ripples through the astrobiology community. While the detection isn't confirmed, it showcases how atmospheric chemistry alone could betray life's presence. The next generation of telescopes, like the Habitable Worlds Observatory, will take this further, mapping not just what gases are present, but how they interact over time. Seasonal fluctuations in oxygen or methane could reveal biological rhythms, while unexpected ratios of nitrogen isotopes might hint at microbial metabolism cycling nutrients globally. Critics argue this view risks anthropocentrism, assuming alien life would mirror Earth systems. But the beauty of the extended Gaia hypothesis lies in its universality. Any life form, no matter how exotic, must interact with its environment to obtain energy and manage waste. Even on Titan, where hypothetical methane-based organisms might thrive, their metabolism would alter atmospheric chemistry in detectable ways. The key isn't looking for Earth-specific recipe, but for thermodynamic imbalances, atmospheres that defy equilibrium, signaling something is actively working to maintain them. This shifts the search for life from a hunt for individual organisms to a study of planetary-scale behaviors. A world with a biosphere might not just host life, it might perform it, with every gas exchange and mineral cycle acting like a heartbeat. Future telescopes could spot these living planets not by zooming in, but by stepping back, reading the symphony of elements in their skies as a score written by biology. The cosmos might be full of worlds breathing, adjusting, and enduring, all without a single engineer calling the shots. And if that's true, then Gaia isn't just an earthly anomaly, she's a cosmic archetype. Stars aren't supposed to come back from the dead, but when they do, they might bring their planets with them. White dwarfs, the smoldering cores left behind when stars like our Sun exhaust their fuel, were once thought to be cosmic gravestones, signaling the end of planetary systems. Yet something extraordinary is happening around these stellar ghosts. As they cool, some white dwarfs are shockingly reanimating their frozen outer worlds, thawing planets that spent eons in deep freeze. It's the ultimate cosmic resurrection story, and it could mean life gets a second chance long after its star has died. Here's the twist: when a sun-like star swells into a red giant, it incinerates its inner planets before collapsing into a white dwarf. Conventional wisdom said any surviving worlds would be bleak, irradiated wastelands, but recent observations reveal a different reality. As the white dwarf cools over billions of years, its gravitational pull shifts, and distant, frozen planets once locked in icy hibernation begin migrating inward. The faint warmth from the cooling stellar core, though minuscule compared to a living star, is enough to liquefy subsurface oceans or even vaporize ice layers into temporary atmospheres. Imagine a world frozen solid for billions of years suddenly sprouting geysers as it drifts closer to its undead sun, like frost thawing on a windowpane held near a dying ember. This isn't just theory, we've seen it in action. Take WD-1856+534b, a gas giant that somehow survived its star's violent red giant phase and now orbits the white dwarf remnant every 34 hours. Its existence proves planets can endure stellar apocalypses, and if a Jupiter-sized world made it, why not an Earth-like one? But the real mind bender isn't just planetary survival, it's the possibility of life rebooting. On Earth, organisms like tardigrades can withstand near absolute zero temperatures and radiation doses that would liquefy human DNA. If microbes were cryopreserved in the outer reaches of a dying system, the white dwarf's gentle reheating might rouse them after epochs of suspended animation. The implications rewrite the rules for where and when life could emerge. Most habitable zone calculations focus on living stars, but white dwarfs could offer stable heat for up to 10 billion years, far longer than the Sun's total lifespan. That's enough time for life to evolve, perish, and potentially re-evolve in cycles. Picture a planet where life arises twice, first under the warmth of a yellow sun, then again in the dim glow of its corpse, adapting to an entirely new energy economy. Perhaps organisms would harness infrared radiation instead of visible light, or rely on chemical energy from tidal flexing as their world inches closer to the white dwarf. The search is already underway. When the James Webb Space Telescope analyzed the atmosphere of another white dwarf system, it spotted traces of water vapor, a hint that icy planets or comets might be evaporating nearby. Future telescopes could hunt for biosignatures like oxygen or methane in these unlikely places. After all, if life can cling to existence in Earth's harshest corners, why not on a world reborn from the ashes of its star? White dwarfs aren't just stellar tombstones, they're cosmic defibrillators, capable of shocking frozen worlds back into the game of life. And if we find even a single microbe thriving in such a system, it would prove the universe never truly lets life go extinct, it just hits pause. Red dwarfs should be teeming with civilizations. These dim, cool stars burn for trillions of years, offering life a runway dozens of times longer than Earth's entire history. Yet when we scan their habitable zones, we're met with silence. No radio whispers, no laser pulses, not even the faintest hint of industrial pollution. It's as if the universe built the perfect longevity engines for intelligence, then forgot to populate them. This eerie quiet around M-dwarf systems isn't just a curiosity, it's a paradox that could rewrite our understanding of where and how life might thrive. The most obvious culprit, stellar tantrums. Red dwarfs are notorious for violent flares, erupting with enough UV radiation to strip atmospheres off nearby planets within millennia. Proxima Centauri, our closest stellar neighbor, regularly unleashes bursts thousands of times stronger than anything our sun produces. Early models suggested these flares would render all nearby planets sterile, but nature loves exceptions. Take TRAPPIST-1, a red dwarf with 7 Earth-sized worlds, 3 in its habitable zone. Observations reveal its flares might actually help life by sparking chemical reactions in underground water reservoirs, similar to how lightning may have jump-started Earth's primordial soup. Yet, even if life survives, could it ever evolve technology under such bombardment? Then there's tidal locking, a quirk of physics that shackles planets to their stars with one scorching day side and one freezing night side. Without a rotating day-night cycle, weather patterns could grind to a halt, turning the Terminator line between light and dark into the only habitable strip. But life isn't easily boxed in. Earth's deep-sea vents host ecosystems in perpetual darkness, while high-altitude microbes float in near-vacuum conditions. An M-dwarf planet's twilight belt might harbor intelligence adapted to a ribbon of stability, its civilizations spreading laterally like moss across a log rather than encircling the globe. Perhaps the most radical idea is that red dwarfs don't need tool users to maximize longevity. Subsurface oceans shielded by miles of ice could be the galaxy's true cradle of life. Europa and Enceladus taught us that liquid water doesn't require sunlight, just tidal friction or radioactive decay. In a permanently frozen world orbiting a dim star, evolution might favor sensory adaptation over manipulation, giving rise to vast, slow-moving ecosystems of pressure-resistant organisms communicating through bioluminescent pulses. Intelligence here wouldn't build radios, it'd optimize survival in the dark, leaving no traces we'd recognize as technological. The silence might also be a matter of perspective. Human technology evolved around metals and electricity, materials abundant in solar systems forged by short-lived massive stars. But red dwarfs form from nebulae with fewer heavy elements. A civilization arising on a planet starved of iron and silicon might leapfrog straight to bioengineered polymers or quantum-scale computing, their signals indistinguishable from background noise to our primitive detectors. Or maybe the answer is simpler. Red dwarfs are old, far older than our sun. any civilizations they hosted could have risen and fallen billions of years before Earth's first microbes stirred. Their signals, if they ever existed, may have already washed over our galaxy like a silent tide, leaving only echoes we're not yet equipped to hear. The eerie silence isn't emptiness, it's a monument to time's vastness, reminding us that the search for life isn't just about space. It's about learning to listen across epochs. Venus taught us a brutal lesson: nature loves to fake us out. That infamous phosphine detection in 2020 wasn't just a thrilling mystery, it was a masterclass in cosmic deception. The universe has a knack for mimicking life's fingerprints, turning what looks like undeniable proof into dead ends. Abiotic processes, chemical reactions without biology, can spoof biosignatures with eerie precision. On Venus, volcanic activity or exotic mineral interactions might have churned out phosphine in ways we've never seen. The cosmos doesn't care about our excitement. It follows its own chaotic rules, leaving us to untangle the mess. This is the biosignature false positive problem, and it's about to dominate the next era of astrobiology. As the James Webb Space Telescope peers into exoplanet atmospheres, spotting gases like methane or oxygen, we can't afford another Venus moment. Take oxygen, often hailed as the gold standard for life. Earth's atmosphere brims with it thanks to photosynthesis, but there's a catch. Abiotic processes can generate oxygen too. Young planets bathed in intense ultraviolet light can have their water vapor split into hydrogen and oxygen, while certain minerals releasing oxygen under extreme heat might mimic biological production. Even Earth's nitrogen cycle, a complex dance of microbes and chemical reactions, shows how easily nature blurs the line between biology and geology. The solution: stop hunting for single, smoking gun molecules and start decoding atmospheric symphonies. A planet with oxygen alone might just be a UV-scorched rock. But pair that oxygen with methane, a gas that should react explosively with oxygen unless life keeps replenishing both, and the case strengthens. Add ozone as a stabilizer or nitrous oxide as a metabolic byproduct, and suddenly you've got a chorus of gases that's hard to explain without biology. Earth's own air is a blueprint. It's not just oxygen that gives us away, but the intricate balance of dozens of gases, each a note in a song only life can sing. This multi-signature approach is already paying off. When JWST analyzed K2-18b's atmosphere, it didn't just report methane. It mapped the ratios of carbon dioxide and hydrogen, hunting for imbalances that hint at active chemistry. The next frontier, temporal monitoring. A planet's atmosphere might look abiotic in a snapshot, but seasonal spikes in certain gases like methane flaring during a hemisphere's summer could betray underground microbes waking with the warmth. The universe isn't just testing our technology, it's testing our imagination. Every false positive isn't a failure, it's a clue, forcing us to refine our cosmic detective skills. The phosphine scare wasn't a setback, it was a rehearsal for the bigger show ahead. Because when we finally spot that undeniable blend of gases, the one nature can't fake, we won't just be finding life. We'll have learned to listen to the universe's subtlest whispers. Imagine a civilization so advanced, they've turned the galaxy itself into their communication network. No radio waves, no clumsy satellites, just stars and subatomic particles whispering messages across the void. This isn't sci-fi fantasy. It's the galactic internet hypothesis, where extraterrestrial societies might be chatting via modulated neutrino beams or exploiting quantum entanglement to send instantaneous signals light years apart. While we're still shouting into the cosmic dark with century-old radio tech, they could be using stars as natural amplifiers, bending space-time itself to relay data with precision we can barely fathom. Neutrinos, those ghostly particles that pass through entire planets like they're not even there, are the ultimate interstellar couriers. Unlike radio signals that degrade over distance or get swallowed by cosmic dust, neutrinos barrel through supernova, black holes, and nebulae untouched. An advanced civilization could encode vast libraries of information in their subtle oscillations, broadcasting to the galaxy without fear of interference. Earth's detectors like IceCube have already spotted these cosmic specters. What if some of those faint pulses aren't just stellar static, but encrypted greetings or galactic news feeds? Then there's quantum entanglement, nature's ultimate cheat code. Particles linked this way can instantaneously mirror each other's states, no matter the distance. While humanity struggles to maintain quantum coherence in lab-cooled chips for mere seconds, a sufficiently advanced species might have mastered quantum repeaters, creating an unbreakable, real-time communication web spanning star systems. No lag, no eavesdropping, just perfect synchronicity. The catch: we'd need to crack quantum decryption to even recognize such signals as artificial, leaving us functionally deaf to conversations happening right under our noses. But the most elegant solution might be hiding in plain sight. Stars as lenses. Einstein predicted that massive objects warp spacetime, bending light around them like a magnifying glass. A civilization could exploit this by positioning transmitters at precise gravitational focal points, turning entire stars into signal boosters. Picture a relay race where each star subtly tweaks and amplifies the message, sending it pinballing across the galaxy with minimal energy loss. Our own sun's focus lies about 550 out, well beyond Pluto, but trivial for a society with interstellar probes. Meanwhile, humanity's radio leakage, everything from old TV broadcasts to military radar, is bleeding into space like a toddler babbling in a library. Those signals weaken to noise within light years, rendering them meaningless. Even our deliberate attempts at contact, like the Arecibo message, are laughably crude, a pixelated shout into the dark. It's the difference between sending smoke signals and fiber optic cables. If the galaxy hums with neutrino symphonies or quantum handshakes, we're not just missing the party, we're wearing earplugs. The irony: we might already have detected fragments of this galactic web without realizing it. Unexplained neutrino bursts or anomalous quantum measurements could be shards of a much larger conversation. Until we learn to listen in the right channels, the universe's most advanced social network will remain a tantalizing rumor, a hum of static that just might be the murmur of distant voices. Imagine planting a forest where every tree takes a century to grow enough seeds for the next grove. That's the essence of percolation theory applied to galactic expansion. The idea that civilizations might spread through the cosmos not in explosive waves, but in sluggish, resource-dripping increments. Unlike sci-fi's warp-speed empires, this model suggests a universe where interstellar travel isn't just hard. It's bottlenecked by energy economics so severe that even a single successful colony could take millennia to fuel the next leap. Consider Polynesia as a terrestrial parallel. For centuries, Voyager's island hopped across the Pacific, not in a single ambitious dash, but in cautious stages dictated by canoe technology and food supplies. Each new settlement had to stabilize before mustering resources for the next voyage, creating an expansion rate measured in generations, not years. Now scale that to space. Even with advanced propulsion, the energy required to send a self-sustaining colony ship to Alpha Centauri could dwarf a civilization's entire industrial output for centuries. Like Antarctic research stations, those isolated outposts where every ounce of fuel and food must be painstakingly pre-positioned interstellar colonies might operate on razor-thin margins, unable to even consider further expansion until their infrastructure matures over millennia. This theory flips the Fermi paradox on its head. The silence isn't because civilizations die out, it's because they're stuck in a cosmic traffic jam, each expansion step throttled by energy scarcity. A civilization might master fusion or antimatter, but if harvesting enough fuel for a colony ship requires strip mining entire planets or waiting for stellar collectors to amass energy over eons, progress becomes glacial. There's a brutal math to it. The energy cost of accelerating even a modest ship to relativistic speeds could exceed the lifetime output of a planet. Factor in deceleration at the destination, terraforming and sustaining the colony, and suddenly, the Great Filter looks less like a catastrophe and more like a spreadsheet. The implications are humbling. If percolation governs galactic expansion, we might not be alone, just isolated by the same thermodynamic constraints holding everyone else back. Civilizations could be sprinkled across the Milky Way like distant campfires, each too faint and far apart to see one another. And while we dream of warp drives and wormholes, the universe quietly enforces its own speed limit. Not the velocity of light, but the patience required to accumulate the energy to move. 4 billion years ago, Earth was a molten wasteland, volcanoes belching poison, asteroids crashing like cosmic artillery, no oxygen in sight. Yet somehow, in that chaos, life emerged. Not just life, but a single organism whose descendants would eventually branch into every creature we know today. Scientists call it Luca, the last universal common ancestor, and piecing together its story is like reconstructing a dinosaur from a single tooth. But here's what we've uncovered. Luca wasn't some delicate pioneer. It thrived in scalding water, feasting on chemicals spewing from hydrothermal vents, building its cellular machinery with metals like iron and nickel. A thermophilic, chemosynthetic survivor, perfectly adapted to a world that would kill us in seconds. Now zoom out to the cosmos. Those same vents Luca called home still gush on ocean floors today, not just on Earth, but beneath the ice of Enceladus, in the subsurface seas of Europa, even on exoplanets light years away. If life started here in such extreme conditions, why wouldn't the universe use the same blueprint elsewhere? Recent studies of extremophiles organisms thriving in acidic lakes, nuclear waste, even the vacuum of space, prove life is shockingly adaptable. Some Antarctic microbes share 40% of their DNA with Luca, despite evolving in polar ice instead of boiling vents. It's a clue that life, once sparked, clings to existence with staggering tenacity. But here's the humbling twist. While the universe might be littered with microbes, intelligence could be its rarest accident. Think of Earth's timeline: single-celled organisms dominated for 3 billion years before multicellular life even got a foothold. Then came 5 mass extinctions, each a roll of the dice where intelligence could have been erased. Now imagine an exoplanet with similar vents, similar microbes, but no asteroid to wipe out the dinosaurs, no ice age to push primates from trees. Life there might stay forever microbial, cycling through endless generations of chemosynthetic slime, never stumbling into consciousness. This isn't pessimism, it's a reality check. We scour the cosmos for radio signals and Dyson spheres, but the truth might be quieter. A galaxy teeming with equivalents of Luca, thriving in vents and ice cracks, never evolving past biofilm. Yet even that vision is thrilling, because if life is common but intelligence is freakishly rare, then every thinking civilization becomes a statistical miracle. We're not just searching for aliens, we're celebrating the cosmic lottery that let us ask the question at all. So where does this cosmic scavenger hunt leave us? 30 discoveries, from the phosphine-draped clouds of Venus to the methane whispers of distant Hycean worlds, tell a story far bigger than any single anomaly. The evidence is mounting. Life's ingredients are universal, its potential habitat staggeringly diverse. Whether it's microbes thriving in acid rain or hypothetical organisms woven from diamond lattices around pulsars, the universe seems obsessed with experimenting. But here's the thrilling part: we're no longer just speculating. For the first time in history, answers feel within reach. The James Webb Space Telescope is already rewriting the rules, sniffing out alien atmospheres with precision that would have been unthinkable a decade ago. Imagine it confirming dimethyl sulfide on K218b, a gas tied irrevocably to Earth's plankton, or spotting seasonal oxygen spikes on TRAPPIST-1e that mirror our own biosphere's rhythms. Meanwhile, Mars sample return missions could deliver the ultimate smoking gun: fossilized microbes in Martian clay, proving life arose independently next door. And let's not forget the wild cards, like a future Europa lander cracking through the ice to find hydrothermal vents swarming with Europan equivalents of tube worms, or a stray radio signal finally breaking the great silence with mathematical clarity. Yet amid this fervor, Carl Sagan's words echo with haunting prescience. Remember the pale blue dot Earth as a speck in a sunbeam suspended in the void. Every discovery we've covered humbles us further, not just by hinting at how crowded the cosmos might be, but by underscoring how fragile and singular our own story remains. Life could be everywhere, yet each instance, whether a sulfur-breathing Venusian microbe or a methane-drinking Titanian cell, will be a product of its own impossible odds, its own version of Earth's 4 billion-year dance between chaos and opportunity. That's the real gift of this search. It's not just about finding neighbors, it's about redefining what it means to be alive in a universe that's far weirder, far more generous with its mysteries than we ever dared imagine. The next decade could deliver revelations that rewrite textbooks, or it could deepen the enigma, reminding us that the universe owes us nothing. Either way, the hunt continues, not just with telescopes and rovers, but with something far more powerful: our relentless, insatiable curiosity. After all, we're made of star stuff, as Sagan would say, and star stuff doesn't stop wondering.